This is PH 3501 Unit 1 Solid State Physics by Dr. M.R. Gadhvi, lecture number 7. Now we are starting the second part of the syllabus, that is about the crystal physics. The same book, Introduction to the Solid State Physics by SSP Lecture, New Age publication, and chapter number 3. Just go through that. So even on the website the topics are mentioned. Anyway, so what is basically solid state physics? In many other books or even this books, where you are finding out the word using it is the condensed matter physics. So solid state physics is commonly also known as a condensed matter physics. The idea behind that is it is a study where you are underlining the behavior of atoms which are very close in proximity to one another, and therefore the any respond to a one atom do reflects on their neighbors, and therefore it is referred as a condensed matter physics. In fact, condensed matter physics is a much better name, since many of the concepts relevant to solids are also applicable to liquid as well. Now, as we are knowing since from the 9th standard that matters can be divided into the 3 category: gases, liquid and the solids. The present study are underlining only the solids. So we will be just lightly touch the gases and liquids, and thereafter we will be focused on the solid in a detail. Now gases, as we are aware, gas have the atoms or molecules that do not bond to one another in range of pressure, temperature and the volume. You also knowing that the molecules haven't any particular order and they move freely within a container. If you look at here, these molecules are just getting reflected from the container. That means they are freely roaming within the container. They take a shape of container, they follow the shape of container and they get reflected from this one. That means they can move in a random way because they are not in the range of any particular pressure or order, and therefore they are doing the Brownian motions. As far concerned about the liquids, it is similar to gases, and liquid haven't any particular atomic or molecular order. They are continuously under the influence of the temperature as well. But still, compared to the gas, the liquid do have a little bit more close approach of such kind of the molecules compared to gases. So in context to gases, liquids are much closer or condensed, and therefore they are partially, not strongly like a solid, but partially do reflect about their close proximity or the nearness, and therefore indirectly we can say that they are loosely bound or they have loosely bonded setup, and which can easily triggered or tackled by the even the temperature, and there it is easily going to be break is also possible. So the futile bonding, and you are knowing that in a liquid it is always the secondary bonds like a van der Waals bonds and so on. Anyway, so now the solids. So the solids material can be further 3 category. One is the crystalline material, the polycrystalline material and the amorphous. If you do remember, then till the 9th or 10th or 11th and 12th standard, this word may not come across in your syllabi, because polycrystalline is a kind of understanding at a higher level education. Now in the crystalline material, that means there is a very specific order are there, as I mentioned here. Each type is characterized by the size of order region within the material. So there is a region where you are finding out the very specific order. The order region is a special volume in which atoms or molecule have a regular geometric arrangement or a periodicity. So there is a well maintained organization of the atomic position and the molecule position. As far concerned about the polycrystalline, the same order and the same arrangement will be at a very lower level or a short range order, whereas in the case of amorphous, one is not finding any kind of a order, or you can say that in some special amorphous material one are finding the order, but they are very up to very short order arrangement, and further you are again finding the randomization. Anyway, in a crystalline material, which is the ordered material, specific material, and having a one more category, subcategory, that is a single crystal. What is amorphous material? As I said just before a second, amorphous solid is composed of randomly oriented atoms or ions or molecules that do not form definite patterns and the lattice structure. This lattice structure, which is underlined here, this word we will just study after 2-3 slides. So just remember for a while and we will cover it very shortly. The amorphous material, or you can remember like this lattice structure, and that is nothing but the defined patterns which doesn't carries by the amorphous. So molecules do not form any defined pattern. Amorphous material have a order only within a few atomic और molecular dimensions. एक या दो एटम तक या मैक्सिमम 3-4 एटम तक उसका ऑर्डरिंग मेंटेन रहता है, उसके बाद it is not sustainable. So amorphous material don't have so. Amorphous material do not have any long order. So वही बात रिपीट कर रहे हैं, तो it doesn't have a long order arrangement and they have a varying degree of a short order in in a one dimension it having a such kind of the arrangement. With the go with the second dimensions they may having a different arrangement. That means as such there is not a periodic or geometric ordered arrangement you are not finding in the amorphous material. So this is amorphous. Very well known examples are the plastics, or you can say the polymers, glasses. Basically amorphous and glass, if you touch the detailed higher education study, then the glass is also a special class of solids where it is lying in between a polycrystalline and the amorphous. So a partial order arrangement of a geometric position of atoms do available in the glasses, but in general moreover glass is considered to be the amorphous material. And nowadays the very well known and hot cake topic, that is a solar cell, and for a solar cell amorphous silicon is widely used. It is also sometimes used in the thin film transistors. What is polycrystalline material? Polycrystalline material is basically a crystalline material, but the size of the crystals are very small, and therefore it is referred as a crystallites, or it is commonly called as a grain, or it is also sometimes referred by the crystallites. So if your material crystalline material is of a very small size, that is known as a grain, then you may find it out many small single crystals also known as a crystallite, and they are aggregates to each other. So it looks like here, look at this figure where this is a group of atoms and here the arrangement is there, well ordered, well maintained, but this is the another region where the order arrangements are different of atoms, they having the same atoms, but the arrangement of the atoms are different from a one grain to the another grain, and so on. And sometimes these grains are also known as a domain. So this is, I think, domain words you have definitely come across in the magnetic material and the varieties of a magnetic material in your either 11th 12th grade or at least in the FY somewhere. So this is nothing but the domain. So here the arrangement of the atoms and their orientations are this not similar to the adjacent domain or the region. So this way there is an order of a geometric order of atomic structures, but it is quite not for a long one, as the crystal size are very small. In general, the grain size are usually in the range of 100 nanometers to the 100 microns. But if this polycrystallites, if you are reduce with their size by some technique and bring it to in between around 9 or less than 10 nanometers, or to be broadly speaking less than 20 nanometers, then such materials are known as a nanocrystalline material, or nowadays it is known as a nanoscience or a nanotechnology. Using this branch, people are making a very shiny technology, or a future horizons are lying on the nanotechnology. That might be you have heard also. Okay, so the crystalline we have seen, we have seen the amorphous material, we have discussed the polycrystalline, and now the interesting or the part of syllabus, that is a crystalline solids. So what is crystalline solids? In a solid state physics, we will dealt with the crystalline solids, and that is a solids with a atomic structure based on a regular repeated patterns, or it is also known as a geometric orientations. And many important solids are always you are finding out the crystallines. We have also observed that compared to amorphous as well as compared to the polycrystalline, the crystalline materials are well studied and well explanatory, because their atoms and molecules are very ordered, and you can make a calculations for their easier for such kind of the materials, and that would be easier also. But in case of amorphous and the polycrystalline, it is difficult to understanding their behaviors immediately, just like a solid one. It's not that easy, because their order arrangements are not that specific as you can see in the crystalline solids. Okay, so there was a word about the lattice. So basically what is lattice? Now onwards the lattice word become very much common, and we will study it continuously. If you do remember in the previous chapter of your chemical bondings and so on, then this chemical bondings are basically the bond between the two atoms or the two molecules. And if I want to visualize in a space, then this kind of the patterns will be supported by the any coordinate system or any periodic arrangement in the directions in the space, and this is known as a lattice. So basically a lattice is a mathematical tool which is used to indicate or pinpoint a position of an atom or the space which is define the position of an atom or presume the availability of atoms are known as a lattice points, and such points in the space is called a space lattice, or sometime it is used other word lattice space, and commonly called a crystallites. So like here there is a one atom, so this all green dots are basically just a simply a points in a two-dimensional mathematical graphical representation. This is x-axis, this is y-axis, and on x-axis and y-axis I can make just making a pattern by dot. Now on this dot, if I will represent availability of atom, then ultimately I can avail a coordinate or position of the atom A, and therefore I can have the each and every detail of wherever the atoms are available on this lattice pattern. I may have their coordinates. If I do have a coordinates, I can see the distance between them and what is the orientation of them, and that is why the crystallites are always well ordered geometrical study. And to just have a platform of a lattice points or a space lattice, you can visualize the availability of the atoms and their structures and their orientations. So basically a lattice is nothing but a mathematical concept which help us to give the coordinate system for the availability of the atoms in a space. Let us say I do have a one crystalline system and I do have a amorphous system. Why crystalline system can be studied easily? Because if I will put a coordinate system for each and every atom, I having a very clear vision, I having a very clear identity about the availability of atom. But if I will go with the amorphous, and if the using the same coordinate system, I don't find any particular orientation throughout the axis. I am not finding any particular periodicity of the atoms throughout the axis, whereas over here in the case of a crystalline, one can speculate very order arrangement of atoms. Crystallite lattice. Crystallite lattice is basically a space lattice which defined as a regular distribution of points in a space in which every point has an identical surrounding as any other points in this array. That means a space lattice defined as a regular distributions of a point. So this all are the points are nothing but the space lattice, and every point has their identical surrounding. That means if I am looking from this point, the surrounding is identical compared to the point C. So point A, point C, point B and their surroundings are basically identicals. So there are such 14 types of possible lattice, and that is called a Bravais lattice. On basis of this 14, the question may arise that how this 14 Bravais lattice are only possible, and this 14 Bravais lattice are only possible because of their orientations, their symmetry and their surroundings. So symmetry is basically their surroundings. So on basis of their symmetry or their surroundings, they can maximally categorize in the 14 varieties. So in all the crystallites having a varieties of 14 lattice only. So अभी जो भी till the date whatever the study is carried out, all varieties of the crystallites are within this 14 lattice pattern. Okay, so the array arranged exactly in a periodic manner. So this all arrays are very well defined and very nicely arranged, and each point of a lattice is called a lattice point or a lattice site where you are placing the atoms. Now in this lattice point, if you are making the smallest pattern which is periodically repeated throughout the lattice point. So if I will look at that, I will make a group of 4 or 5 atoms, and this group of 4 and 5 atoms are periodically repeated throughout my lattice pattern of x axis in the direction of a y axis in a direction of a z axis. So the smallest group of atoms or molecules which is very periodically organized which is known as a unit cell. So I am mentioning here unit cell is the smallest portion of a crystal lattice which when repeat in a different directions generates the entire lattice. That means this small group of atoms or a smallest part of a crystallites which is periodically repeated along the axis. I can give you a fundamental example like a wall of your house or a room, and if you look at that, then the bricks within that wall is periodically repeated throughout the length breadth of your wall. Now wall is a two-dimensional property, so if you look at the x-axis, if you look at the y-axis, you can find it out there is a periodic repetition of the bricks after a certain interval. That means the bricks is kind of a unit cell of the entire wall, and that's how it is working. So unit cell is a basic structural unit or a building block for any crystalline structures. Lattice is made up to represent the unit cell, and as I said earlier, lattice is basically a mathematical tools which help us to assume or presume the availability of atoms, and once they have a mathematical tools, so it is also supported by the coordinate system. That means when you have a unit cells, it having a 6 lattice parameters. So any unit cell having a 6 lattice parameters, 3 parameters about their length of the unit cell. So this blue line figure is basically a unit cell, that is a building blocks, that is the smallest and periodic repeated arrangement of the crystalline system. That is what the blue line over here, which is referred as the unit cell, and it has a 6 parameters which is referred as a lattice parameter, and that is along the x-axis the unit vector are referred as a along the y-axis the unit vector are defined as a b, along the z-axis the unit vector along to that is referred as a c, and the angle between this all the line segment, this all the lattice vectors, that is a, b and c, are also having a angle between them which is may also differ. As I said, there is a 14 varieties of the Bravais lattice, so thus 14 varieties lattice having a this a, b, c, that is the lattice vectors are different, as well as the angle between them, that is the alpha, beta and gamma. So in between b and c it's a alpha, in between b and a that is a gamma, and in between a and c that is a beta. So all these three angles and these three line vectors, that is a, b, c, that makes 6 lattice parameters. So any particular structures having a unit cell and each unit cell having their 6 lattice parameter. So on the basis of lattice parameters one can define a type of a structure of the crystallites material or crystalline material. Now there is a two type of a unit cell. One is called the primitive unit cell and another is called the non-primitive unit cell. You can see there is a in this two-dimensional figure P are mentioning about the primitive. You can see there is a different shapes are there, and there are some other different shapes, but they having a more than 4 or more than corner. There is a one more dots are also available, so one more additional lattice points are there. So on that basis they are categorized as either primitive unit cell or the non-primitive unit cell. Let us try to understand the definition. The primitive unit cell must have the only one lattice points. The question arises how it is possible. Let us say it's a two-dimensional. That means each corner atoms having the contribution to this particular shape, that would be 1/4, because there is a 4 corner. So the contribution of this dot is 1/4 towards this particular shape. About this corner is having a 1/4 contribution towards this particular shape. So this particular parallelogram, and each corner of that one having a contribution of a 25%. So 25%, that is 1/4 multiplied by 4 atoms. So ultimately 1 atom, or basically a 1 lattice point. So if any structure, and if any unit cell having the availability of atom contribution or a lattice point is only 1, then such unit cell is referred as a primitive unit cell. Here you may have a different shape. As I said, there is a 14 varieties of Bravais lattice. That means the shape of the unit cell could be different, but the available number of atoms will be again 1 only. यहाँ पे आप देखो, यहाँ पे 4 corner है, but the parallelogram and their angles are quite different compared to this. But the available number of atoms here also of 1, here also 1, or available number of lattice points here also 1, and here also 1. If you look at here, then I chosen a boundary such that so entire lattice point P is within the boundary. But in a way, there is also a 1 lattice point within the chosen shape. That means wherever you having only 1 lattice point, it is called a primitive unit cell. Whereas if you having a more than 1 atom or more than 1 lattice point of a lattice space, then such unit cell are referred as non-primitive. If you are looking here, so 4 are cornered, so that is a 1/4 contribution of each corner. So 1/4 multiplied by 4, so it become a 1, and plus 1 lattice point entirely inside the center of this lattice unit, two-dimensional unit cell, and therefore it is 1 plus 1. So it's a 2 lattice points are there, and which is not equal to 1, and therefore I can tag this as a non-primitive unit cell. Similarly over here, so 4 corner is the contribution of, let us say, 1/4, and this is a side wall, so the contribution is, that is will be the 1/2. So 1/2 plus 1/2, so it become 1, and this 4 corner is also become the 1/4 into 4, that is 1. So in all there is a 2 lattice points are involved in this, and therefore it is more than 1. So it's again non-primitive unit cell. So primitive unit cell in a 3 dimension. So this is a primitive unit cell. So I have a vector A along the x-axis, vector B along the y-axis, and vector C along the z-axis. And I also told there is also the angle between them are also very important. Okay, so what is this? The primitive unit cell is made up of a primitive translation vectors, which is referred as A, B and C, which are respectively aligned with the x-axis, y-axis and z-axis. There is no cell of a smaller than this volume, because it's a fundamental blocks. It's a unit cell, so lesser than, smaller than this size is not possible. So for any crystalline material, the smallest size is always, or the smallest volume is always the unit cell. A primitive unit cell will fill the space by repetition of suitable crystal translation vectors, this defined by a parallelepiped A, B and C. The volume of a primitive unit cell can be found by A dot B cross C, because as you are knowing that this is B cross C, that means this vector is crossing with the C vector, so it will give you the area of this plane. And if area of this plane is multiplied by throughout the length of the vector A, so ultimately it will gives us the volume of this one. So the A dot product with the result of a B cross C, B cross C will gives us the area multiplied by the length of the unit cell, so that would be the volume. So ultimately it's a L into BH. So that is how we are getting the area. If it's a cubic one, then it would be, this is also A, this is also A, and this is also A, because A is equal to B is equal to C in case of a cubic, and therefore volume can be given by A to the power 3. Now there is also another well known word are coming, that is called the basis. So basis and crystal structure, very nice definition given by Charles Kittle, and it is also a very well known book, Solid State Physics by Charles Kittle. You can read it at least once you finish the S.O. Pillai. It would be easier to remember the Charles Kittle. Now he has given a very nice definition for any crystal structure. It says that it is a crystal lattice plus basis. So this is another word you are learning in the crystal physics, or a condensed matter basis. Basis, that means it could be a single atom, or it could be a group of atom, or it could be a molecule. So a basis are located at your crystal space or a lattice space, and that is known as a crystal structure. As I said that lattice is basically a just points in a space represents with the coordinate. Over there you are placing the availability of molecule or group of atoms. So wherever I have a dot, I am placing this pair of atoms or molecules. So this is my crystal structure, a periodic repetition along the x-axis, a periodic repetition along the y-axis, and same way in a depth, that is a third dimension, also you will finding the same one. So crystal structure can be obtained by associating atoms or a group of atoms or a molecules, which is called the basis, and this is nothing but it is all referred as a pattern in common literary word. There is also one very well known word for basis, and that is motif, MOTIF, motif. So either a motif plus crystal lattice gives us the crystal structure, or a basis plus crystal lattice gives us the lattice structure. So basis is basically an identical composition of arrangement and the orientations. Basis is a single atom of a Na or a copper, or it could be a diatomic also, like in case of Na and Cl, cesium and chloride, or it could be in a triatomic also, and calcium and fluorine too. So it's a combination of three. So basically basis doesn't have a limitation of a group of atoms, but basis is the means, that means it is a group of atoms or molecules which are lying on the lattice, and that makes a periodic repetitions you can visualize in the lattice space, and that is what the mean of structure or a crystal structure. If I want to see a unit cell in a 3 dimensions, so it looks like this. So it's a 3-dimensional unit cell. There is one video I have put it over here in my this presentation. So if you will go through this video, it will help you out. This is not mine video, but it is a standard YouTube video which will help you out to understand how exactly the unit cell, how exactly they are arranging in a lattice space. So it's a nice inner view, and your insight will be increased. So this is a building blocks in a 3 dimensional in a box type, it looks like this. It is a one way of a representation. This is a front elevation, this is a vertical elevation. So unit cell can be represented like this. Thank you very much for paying attention. Stay home, stay safe, be focused, and try to submit your assignment